Hello friends. The course of abstract algebra actually starts with the study of groups. You have seen what groups are. Groups is a very general and powerful structure, and it mainly encompasses of different sets like integers, polynomials, matrices, functions and symmetric transformations. Now, having studied groups, now you are ready to see what rings are. So here we are going to start with the introduction of rings. Rings are specific structures with added operations on groups. So before going to the textbook definition of a ring, let us see some examples. Let us see four sets which are integers, set of real numbers, then a set of matrices of order 2 by 3, 2 by 3 matrices with real entries, and the set of polynomials over complex coefficients. Okay, so in arithmetic we are familiar with four operations, and they are addition, subtraction, multiplication and division. So let us see on these four sets which of these four operations are available. So when we see the set of integers, we can perform addition, subtraction and multiplication to get another integer, whereas we cannot perform the operation of division that will give you a fraction which is not an integer. Now coming to the set of real numbers, we see that all these four operations are available there. Now considering the matrices, the set of matrices of order 2 by 3, we can see that addition and subtraction are available, whereas these two are not available. The matrix multiplication is only possible when you have compatible order for multiplication. So if you have a matrix of order 2 by 3, you can operate it for multiplication with matrices of order 3 by n for any n. So these two operations are not available. Now the last set, polynomials, you know it is available. These operations are available: addition, subtraction and multiplication, whereas division is not available on this set. Why? Because when you divide two polynomials, you end up getting a rational function and it is not a polynomial. So now we will be thinking about the operations of negation or the subtraction or division or the algebraic structures. So in the abstract algebra, we normally use the operation subtraction as, so your operation subtraction in an abstract algebra is treated as the inverse operation of addition. That means if you have 3 minus 7, you can consider it as 3 plus of minus 7, or else 5 minus 3 can be written as 5 plus of minus 3. So actually in abstract algebra, your subtraction is actually replaced by the negation or the inverse of addition operation. In the same way, you can see your division also as the inverse operation of your multiplication. So 5 by 3 is equivalent to saying 5 into 1 by 3. So in abstract algebra, you are having two operations of addition and multiplication. So you might be thinking, what is the advantage of having these operations? That is because in abstract algebra, all the sets that you are going to consider are not always numbers or numericals. We may have the set of symmetries or the set of permutations, for example. When I say you add or subtract two permutations, the meaning is you operate the inverse of the permutation with the given permutation. Now, we can see we will be using the terms additive inverse and multiplicative inverse for the terms that we have used here. Now going back to the 4 sets that we have defined, we can see that here all the 4 sets are groups under addition. Rather, I would say they are commutative groups under addition. And one of them is a commutative group with multiplicative inverse, which is the set of real numbers. So we need names for all these sets with these operations. Now we are ready to go for this textbook definition of rings. So the rings are commutative groups with an additional operation, multiplication in it. So let us see the formal definition. So in rings you have a set R with 2 operations which you call as addition and multiplication. So under addition it should form an abelian group. That means the 4 properties are satisfied. It is closed under addition. It is associative. The 0 element exists. The inverse exists in addition, that is additive inverse exists under addition, and also it is commutative. That means A plus B is equal to B plus A for all elements in R. Now coming to the multiplication, it is definitely closed under multiplication and the property of associativity holds. The property of commutativity, inverse in terms of multiplication, and the existence of unit element in multiplication are not required for rings. So we often call the rings with commutativity satisfied as commutative rings, or commutative ring with unit element when the unit element is present, or else rings with unity when you have a unit element present.